muy bien, me gusta. Ya estamos en directo. Y luego, José, hemos dicho que para las preguntas sí que abre por ahí y vale. El micro lo va a pasar. ¿Este funciona? Hello, hello. Vale, ¿puedes hablar por aquí o por aquí? Pero para las preguntas, habla por aquí y pasamos eso. Okay. Me levanto yo y todo. ¿Estamos ya? Daré una señal cuando te queden 2 minutos. Okay, I think. Hello, hello. Okay, I think we have enough break. We're going to start with the contributed talks now. The first one is by FJ Matute Cañadas from University Autónoma of Madrid. And he's going to talk us about the quantum circuits with multi-terminal Josephson-Andreev junctions. So, the floor is yours.
So, thank you, José Luis. I would also like to thank the other organizers for this opportunity. I feel very happy to be able to participate in the workshop. Just so you have an overview, in the remaining talks of this morning, we will have topics related to the hardware of quantum technologies, mainly condensed matter and specifically superconductors, most of them. So, in my talk, I would like to tell you about superconducting quantum circuits with multi-terminal Josephson junctions. And I will try to do it from two perspectives. First, the relation to the attempt to reconcile these two descriptions of a Josephson junction. A description, macroscopic description in terms of the bosonic degrees of freedom of the circuit where the junction is embedded, and the microscopic description in terms of the fermionic states, the Andreev-bound states, that inhabit the junction itself. And the second perspective, it's their relation to their applicability for the design of protected qubits, protected against decoherence. This is a strategy alternative or complementary to quantum error correction, where you use several average or low quality qubits to create one good quality logical one. No? So before starting, let me just acknowledge and thank Leandro, Alfredo, my supervisor, and all these colleagues and friends we are so lucky to work with. So let's start from the microscopic description. You know, a Josephson junction is just you have two superconductors and connect them by something that is not a superconductor. And as you can imagine, the electrons and holes in this normal region, if they have an energy lower than the superconducting gap, they cannot penetrate into the superconducting leads, no? So they just reflect back and forth. One of these reflections is the Andreev reflection, by which an electron comes back as a hole, injecting a Cooper pair. But the system is quite similar to what's going on in a conventional potential well. There is a set of states, discrete energy states, bound to the junction or to the well. These are the Andreev-bound states that already Alberto introduced. So you see here an example of a system with two pairs of these Andreev levels. These are their energies as a function of this parameter, the phase difference. That is something you can control when you put the junction in this superconducting lead, superconducting ring. Particularly, this comes from one of these fancy materials, indium arsenide, indium antimonide, with a lot of spin-orbit interaction. That's why they are spin split. This is somehow the fine structure of such an artificial atom. Well, if you want to see other fancy Andreev levels, you'll have to wait to the talk by Carlos, where you will see these flat Andreev levels. But maybe your question is how to prove this experimentally, this system, this atomic artificial thing. Well, you can do an spectroscopy and try to excite different transitions, like you may excite a quasi-particle from one Andreev level to another one. You can break a Cooper pair and excite two quasi-particles at once. And of course, in real life, well, the results, the spectroscopy is much more complicated than what you expect. That's why in our desperation to try to label and identify these lines, we like to put them names. So for instance, these ones that have 8 legs, they are the spiders. These ones with 2 palms are the camels. We also have their cousin, the dromedary. And if you look at this spectra for a long time, you can become crazy and begin to be inspired by Darth Vader. But we will not go through that path because I have to tell you a little bit about the other description. But please bear in mind that the way I will do it is not equivalent directly to the way I introduced the Andreev levels. So don't try to find a correspondence for the moment. For the moment, just imagine a piece of superconductor, large. So it's not so different to a coherent light state. You can put another Cooper pair and it will be kind of the same state. But if now we reduce the size of the superconductor, you have a superconducting island that may be capacitively coupled to its environment. And then the number of pairs in the island matters. And this can be described with a charging Hamiltonian of this way that goes with the square of the difference between the number of pairs in the island and what could be the value for an electrostatic equilibrium, which is something you can control with a nearby gate or something. So you see here an example, an instance of an island with certain number of Cooper pairs as a function of this parameter. And here in other colors, other states from other instances with different number of pairs. If the island is isolated, then these are disconnected, no? But if now we connect the island to another superconductor by means of a Josephson junction, then it is able to exchange pairs between them with a probability proportional to this parameter EJ, Josephson coupling. So now the wave functions are coherent superpositions with different number of pairs in the superconducting island. This system implements in some regimes of their parameter 2 very well-known qubits, Cooper pair box and transmon, when EJ of DC here is small or large. Let's focus for the moment just on the spectra. If we want to implement a qubit with the 2 lowest energy levels, you see here, now imagine also that maybe there is some environmental noise in this parameter. During the operation of the qubit frequency will probably change a lot. This is bad. But here in this situation, it will be maintained stable. This is why it is protected to dephasing, which is one kind of decoherence. However, if we look at the wave functions, now in this case, they are more one on top of each other. So, that's why, it is possible for them to relax or to relax from the excited to the ground. So this so difficult. This regime is not protected against relaxation, which is the other kind of decoherence. So, well, it went long. Anyway, forget. It is impossible with qubits, with superconducting circuits with just one mode to have a simultaneous protection against these 2 kinds of decoherence processes. But people are trying to engineer some circuits that have more than one element, and they will be able to have such a simultaneous protection. So our approach is to try to do that, but instead of with multiple elements, just one but multi-terminal Josephson junction. Already in this kind of graphical argument, you see that it is able to mimic the combination of one mode, the transmon that I already explained to you, and the other mode, the fluxonium, which is another kind of qubit where you put the junction in a loop. So indeed, we can solve this system and find some parameters in which the system is protected both against dephasing, because you see here the energies, the qubit frequencies are very flat against these external parameters, and the wave functions are very disjoint. That means they can't relax one onto the other. So it is also protected against relaxation. This, by the way, is an implementation of a 0-pi qubit. Sometimes with this macroscopic description, you can describe a lot of systems. But if you want to do circuits with fancy nanowires, as the one Alberto was using in his talk, we really need to take into account the Andreev structure. So let me give you a brief overview on how we can do that. The simplest situation is, for the bosonic part, a single superconducting island, and for the fermionic part, a single level quantum dot. And between them, there is a coupling that reads as follows. Take a Cooper pair out of the island and put it into the quantum dot. With this, you take it out, and with this, you put the 2 electrons in the dot. And you do the same with the other one. It is quite convenient to interpret these systems as if they were crystals. So without Andreev structure, in the crystal, each unit cell represents the number of pairs in the island. And when you couple the island with the other superconductor, these sides are coupled. However, with a single level quantum dot, now the cell has 2 atoms in the unit cell for empty and doubly occupied quantum dot. And we recover, in this regime, something similar to the transmon. That's why we like to call them Josephson-Andreev transmons, or Hammonds, which is very convenient for this Spanish workshop. Anyway, if you are wondering, what can you do with a third island? It's just playing the same game, but now you live in a 2-dimensional space. Unfortunately, you have to do this kind of configurations if you want to implement a protected qubit, but it will be somehow this protection coming from the bosonic sector. Another question could be, can we have intrinsic protection just from the fermionic sector? This is having a fancy Josephson junction, but only with 2 terminals, now in a circuit with finite inductance and capacitance. And the question is yes, and the answer is yes, but I can't give it to you. You'll have to visit the poster by Diego, where they're trying to implement this qubit called the Fervo. You see that also the wave functions are disjoint, so it will be protected against relaxation. If you like the other parity sector, you'll have to talk with Jose Luis, the chairman here. And if instead of typical Andreev, you want Pursman-Majorana, which are some topological Andreev somehow, you'll have to talk with Michel here, another organizer. So finally, let me just summarize. Probably having protected qubits is useful if you want to have a quantum computer, no? Typically, you do them using multi-element circuits. We have seen there are other alternative approaches, like using multi-terminal junctions, and very different ways, which involve using the fermionic structure of the Josephson junction itself. And just to finish, let me just advertise that in the Autónoma, there are open positions for PhD for projects that combine both theory and experiment. Let me say that it is one of the few places where you can do real-life work on circuit QED. So if you're interested, please write to Eduardo, Alfredo, or talk to me if you want afterwards. Thank you very much.
So, questions? Any questions? I really encourage you to ask anything. Do not hesitate. This workshop is for that, so any question is valid. No? I have one. Can you tell us a bit the differences between these odd and even parity states of this
Sure.
fair one fluxolmium qubit?
Indeed. Well, already Alberto was mentioning, sometimes you have a quasi-particle trapped in your system. So your system can be, this is the ground state, this is even parity. In a superconductor, you only have 2 parities, no? Because Cooper pairs go in pairs, no? The name is here, so. Or you have even number of electrons, or you have even +1, odd. That is one electron that goes like alone somehow. And sometimes one of these electrons from the outside gets into one of these green lines. But other times you can stabilize the system by having this green line downwards. So your ground state will be only having one quasi-particle. So depending on what is your interesting regime, you can play with the Coulomb interaction with the gates to design your spectrum in the way that the parity that you like is the ground state. So most of the population is there.
Okay, thank you very much. So let's thank the speaker again, please. Well, our next speaker is David Caldevila Asenjo. He's coming from Donostia, San Sebastián, and he's going to talk about the experimental observation of multiple Andreev reflections at the interface with a spin-split superconductor.
Well, thank you all for being here today, and thank you to the organizers for letting me present a little bit of my work. Well, let's dive into it. What I'm going to talk to you about is fully experimental, and it's about a superconducting tunnel junction. So the geometry is like this. So we have two superconductors separated by an insulating barrier, and we know that under conventional conditions, nothing else added, so the density of a state for a standard BCS superconductor looks like this. So we have a gap of forbidden energies around the zero energy, where we have the Cooper pairs inside, spin up and spin down, so the green and blue balls. And then we have at the gap, at the energy of the gap, we have the quasi-particle peaks, where we have already the electrons, and these electrons are spin up and spin down. There's no spin preference there. Now, situation changes if we put one ferromagnet next to one superconductor. So now there's a magnetic interaction that is gonna, in one electrode, is gonna change the spectroscopy in a way that now our quasi-particle peaks are separated in a spin up or spin down. And the amount of this separation, sorry that I cannot point, is the H value, which is our magnetic interaction. And this is the system we are going to study, the junction on the right. And just to tell you the materials I'm using, aluminum is the superconductor, and European sulfide is the ferromagnetic insulator. Now, and this is how the junctions look like in real life, let's say. Here you can take a look at the thickness and the geometry. An important thing to say is that this magnetic interaction, in order for it to work and to survive, you need a very good chemical contact between the ferromagnet and the superconductor, which means that all these samples are grown in situ using ultra-high vacuum techniques, which means that we also need to produce the barrier ourselves. And this is an advantage because we are producing the barrier ourselves, so you can change the properties of this barrier somehow in order to make it more or less insulating. And if you make it transparent enough, you can start to resolve subgap transport processes like typically under reflection. So this is strongly related with this underbound state that you just heard about. And very quickly, so under reflection, basically you have a metal and a superconductor. Electron arrives to the superconductor. It cannot penetrate because there are no states available for electrons. So it's going to induce a Cooper pair, and then a hole is going to get retroreflected. Now, if you have another superconductor on the left, this hole can also induce another Cooper pair on the left. And then you can think of it as an electrode trap in the barrier producing Cooper pair left and right. And this is what is called multiple under reflection. And according to the number of bounces that you have different orders. And this is what we are going to talk about. Now, taking a look at the data, so I'm measuring, well, I didn't mention it, sorry about that. I'm measuring transport, basically 4 points, as you can see on the scheme on the figure. So applying current, measuring voltage. And from that, we take the numerical derivative. And this is how a standard curve looks like. The raw data is the black curve, and then the derivative is the red one. And the difference between these two data sets is the growth conditions of the ferromagnetic layer. So we can change first of all, we resolve this splitting, these double peaks that we were seeing. Remember, BCS one peak, splitting two of them. And the distance increases according to this magnetic interaction, which is something we can control on the growth. But also, we found on every sample this third peak that was always at the same energy, independently of the magnetic behavior. And for us, at the first we said that this was the second order MAR. And just let me talk to you a little bit about this second order MAR. So coming back to the MAR, second order MAR means one under reflection, basically. One electron from the left goes to the right, produces a Cooper pair, and then comes back to the left. And on the other way around, from right to left. But the important thing here, is that because the starting point and the end point is the same, because there's only one bounce, so it starts on the left, finish on the left, the spin split, it does not affect this process. Which means that we are going to have a couple of peaks at the threshold energies. That is exactly the superconducting gap. If you do the math, it appears. It's really simple. Now, so in order to see more interesting scenario, we need to increase the transparency. And this is what we did for another sample. And your spectra goes from there to there. And this is the first, as far as I know, the first experimental proof of subgap transport in a spin split system. And now I'm going to explain this, how this line cut works. But before that, let's think about the n equal 3, so an extra reflection. We talk about n equal 2 left, n equal 3 right. Now there's an extra reflection. So when the hole comes back to the left, it's going to induce another Cooper pair and then finish on the right. And now, because the starting point and the end point are different, now the spin split matters. And you can have two processes for a spin up or a spin down. And these processes are affected by the magnetic interaction, H, remember, according to that equation. So now if we perform a theoretical simulation, considering all these properties, this is how the comparison between data and simulation looks like. So simulation red, data orange. And even though in some cases the intensities are not perfectly matched, what I want you to focus is that for every peak that we have in the data, in the orange curve, there's another peak on the red one at the same energy. So this is telling us indeed that we are seeing a multiple under reflection on our system. And I label by colors each order. And right now, for the n equal 2, before was only one peak, now there are two, simply because the deltas for the sample are different. But this is now the spin split. The spin split is n equal 1 and n equal 3. And this goes so on and so on. And then, as a final check, we compare data and simulation on the thermal evolution of the system. First of all, we did a fast transition measurement. We indeed see that with europium sulfide, the transition happens before due to the magnetic interaction. So that's OK. And then we took out the constant in order for the simulations, and then we compare both data and simulations. And again, we were very happy to see that both behaves as, well, the data behaves as the simulations predicted. So there was another check that our system works as should be. And to wrap up with the conclusions, first of all, we were able to grow a reproducible magnetic change splitting in our superconductors, which we can change these H with the growth. Second, we were able to increase the transparency of our devices in order to resolve subgap transport. And lastly, we developed a theoretical model that compares data and simulation and is able to explain and to reproduce the data we are seeing. And with this, let me thank all the people that was involved in this project. All the theoretical framework was done from the people in Madrid here, as you can see here. And thank you all for your attention. And if you have any questions, please go ahead.
Thank you. Questions now?
Thank you for the talk. Interesting. In some other talk, I've seen another explanation in a different system of like the 3 peaks. And that can happen if you have some sort of spin-orbit coupling or tunneling to different spin species, which I think is kind of hard here since you just have a bare superconductor. But can you imagine some spin flipping mechanism that you can have between two superconductors that you have? That's one part of the question. And the second part is, so you could verify if that's really MAR or not, if you are able to magnetize it at a different value, for instance, so that you are split less, or things like that. Did you do checks with this?
Yeah. So first of all, the spin-orbit coupling we didn't consider because we have aluminum. So it's something we forgot about that. Spin flip processes in the theoretical framework. I cannot give much details because I didn't do it. I'm the experimental guy, but you need to consider spin flip processes, but you only take into account on the electrode that is proximatized by the ferromagnet. The problem, well, not problem, but the condition here is that the upper electron, so S2, we take it as PCS standard aluminum. So for that, there is no spin flip, no interesting scenario here. In order to think about these spin flip processes, which is something that I'm trying to do now, is to drop another ferromagnet on top. Then you have two magnetic interactions and you can play around with them. But for our work, we didn't consider that. And with the magnetization for the mark, we indeed play with the magnetization. And I think maybe this data here. We also have the comparison with the simulation. Yeah, that one. So it's the one on the left. Okay. So that's the experimental curve. Maybe I don't have everything one, but it's kind of similar. It's a little bit messier because when applying magnetic field, I had these small blue regions on the left. Yeah. These are pure experimental noise based on, I think, some magnetic twitching weird things. But on we also had some simulations with the magnetic field and it worked accordingly.
Yeah, but I think this is very convincing. I mean, the Mars is very horizontal, so.
Yeah, it goes down, and this 150 is the value at where the transition happens for the lower electron. So then you have NIS.
Okay. Thanks.
Any other question? All right.
Thank you very much for your presentation as well. Oh. Yeah, I just wanted to ask whether, in general, the spin splitting only affected odd orders of Andreev reflection.
Indeed, it does.
Okay.
Okay, my explanation, which I think is the most intuitive, is like for the even orders, so there's an odd number of under reflections, so the starting electron at the end hole start and finish at the same time, at the same point. So the spin split, it doesn't matter. The way to really do it is that you need to draw this diagram and be careful with, you put the bias and you do the calculus that this reflection needs to be symmetric with the Fermi level. And indeed, you will see that the threshold energies for the n equal 2 is just the delta values. For the n equal 4, it's a bit more difficult, but it's not affected by the spin split. Okay. It only happens when you have an odd number of single particle involved, because then you can have this extra particle for the n equal 3. You have an extra electron, can be spin up or spin down. Okay. So that is when you have this effect.
Right. Thank you. Thank you very much.
More questions? No? Okay, then let's thank the speaker.
This one, right? Yep.
Okay, son 12 más 3, ¿vale? Para las preguntas. Perfecto. Por ejemplo. Mira que esté todo bien. El pointer. Okay, so the next speaker is Jaime Saez. He's going to talk about the exchange anisotropies in microwave-driven singlet triplet qubits. So the floor is yours.
Yep. Thank you. So I decided slightly changing a bit the title to make it more simple. But today we are going to talk about singlet triplet qubits in planar germanium. So first, probably all of you already know that quantum computers are predicted to outperform the classical technology we have. And there are multiple platforms. We heard in Alberto's talk about topological qubits or the possibility of having them. We also have good candidates as superconducting qubits, ion traps, photons. But today we will talk about spin qubits that they have still many challenges in physics to learn. So why semiconductor spin qubits are good candidates? Well, first of all, they are industry compatible and compact. And by compact, in this case, I mean that they are more than 100 times smaller than a transmon. They also have long coherence times and also fast electrical control. And the idea of the qubit is simple. We need a two-level system, 0 and 1. And in our case, those two states will be defined by a spin. Then, depending on how many spins our system has, we can have different types of qubits. If we have a single spin, our states will be up or down. However, if we have two spins, we will have what we call a singlet triplet qubit. And our states will be a combination of those two spins that can be down, down, up, up, and also the singlet and T0 states. And how do they look like? Here you have a SCM picture of the first spin qubit, where basically you see the electrostatic gates that form two quantum dots, where the holes or electrons will be hosted with two spins. And now, how much did the field change over the last 20 years? The state of the art at the moment for spin qubits hosted in quantum dots, I would say that are these two designs, one in silicon, the other one in germanium. And the largest systems are 6 and 10 qubits, respectively. And the relaxation times are about 30 milliseconds, the phasing times a few to tens of microseconds, and they have great fidelities in order to start trying to do some computations. Today in particular, we will focus on germanium. What is special about it? Well, first of all, in germanium, we don't have electrons, but we have holes. And that brings good properties for our spin qubits. First of all, it has a strong spin-orbit interaction, what means that we can have a fast electrical control. Also, it has low hyperfine interaction, and that means that the coherence times will be longer. Why? Because basically we have our spin, or our two spins, and they are surrounded by other spins, by a spin bath. Then if that hyperfine interaction is smaller, that means that they are more isolated. And also a nice feature of germanium is that it's compatible with superconducting technologies. So there's already a gate-tunable transmon qubit, and also a proximitized quantum dot that is the first step towards an Andreev spin qubit. That is a mix of a superconducting qubit and a spin qubit, trying to combine the best of both worlds. And also one of the great points about germanium is that the progress has been impressive the last 7 years. So back in 2018, the first spin qubit was done in germanium in a hot wire, but just in 7 years, the field managed to get to a 10 quantum dot device with 10 qubits. So the goal for today, for this talk, is understanding the effects of spin-orbit interaction in germanium, because it's an advantage, but it also brings some caveats. So as I said, it allows for full electrical control, but also it brings to the problem some site-dependent G-tensors that depend on the microscopic properties of the device. So that means that every spin qubit we have will be slightly different from the neighbor. And that affects the qubit properties, such as the energy spectrum, the driving efficiency, and the noise susceptibility. Then this spin-orbit interaction will also induce a tilt in the quantization axis of our spins, and also an isotropic exchange interaction that I will talk about later. But these two are potential problems for scaling up, and it has beautiful physics behind. So the outline for the talk, the two questions that I want to address today is having two spins in a double quantum dot in planar germanium. First, if we have a magnetic field, will be our two spins aligned or not? Then the second question is, can we control the relative tilt in case that they are tilted? So are they, okay, are they tilted or they are parallel? So the idea of the device is actually really similar to what Alberto showed us in the first session. So we have a two-dimensional whole gas that is germanium, sandwiched in between two silicon germanium layers, and on top we have different electrostatic gates that can confine a quantum dot, and we can control how many charges this quantum dot hosts, therefore how many spins we have. And then we can control this spin over here with a microwave source. That would be the cross section. The top view looks like this, where on the bottom part of the device, we have a double quantum dot. We drive from one of the barriers, and on the top part, you see a charge sensor that basically is another quantum dot that we use to sense what is happening on that side and to be able to read out the spin of our system. So we can tune a double quantum dot, and this is a zoom in of an interdot. In this plot, you see on the x-axis the voltage on the left plunger, that is that gate there, right plunger on the other one, and you see 4 different colors. So each abrupt change in the color indicates a change in the charge occupation of our double quantum dot. Then we can go from a 1-1 occupation, so 1 spin there, 1 there, to a 0-2 occupation. So we are sensitive to the charge state of our double quantum dot. And in order to operate our qubit, we will move along that line. But if we are sensitive to the charge occupation, how can we read out the spin state? So in order to do that, we make use of Pauli's spin blockade that is based on Pauli's exclusion principle that basically tell us that we cannot have 2 spins in the same quantum dot with the same direction of the spin. The idea is the following. So we can start in A, so in that point over there with 0 spins and 2 spins on the other dot. We move to point B in this diagram, and then we apply a driving. Then there are 2 options, that our spins are anti-parallel or that they are parallel after the driving. Then we can go to our readout point, C, and then if both spins were anti-parallel, that spin can tunnel into the other quantum dot, and we will get low signal, so that light blue color. If both spins were parallel, this spin cannot tunnel into the other quantum dot because it's spin blocked. That charge state will be 0-2, and we will measure a high signal. When we perform this experiment, and by the way, this is called spin to charge conversion. When we perform this experiment, now you will see here that blocked triangle appears with high signal, and that is the signature of Pauli's spin blockade. So now, once we have this, we want to find the qubit lines. The idea is that we sweep the external magnetic field and the frequency of the bars, expecting to find 2 resonances, as in that plot, one for the left spin, one for the right spin. However, what we found out was slightly different, so there are more than 2 lines in this zoom in. You can see even 4, but I will just talk about those 3. And also the lines do not go to 0 magnetic field, to 0 frequency at 0 magnetic field, and that is the sign of exchange interaction. In simple words, exchange interaction is just how much our 2 spins are interacting, or in other words, how much their wave functions overlap. But what is the nature of these 3 transitions? Because if we expected 2 and we have 3, there's something that we overlooked initially. In order to understand that, the easiest approach is just to plot the energy diagram of a double quantum dot with 2 spins as a function of magnetic field. So at 0 magnetic field, we have a singlet and the 3 degenerate triplets that they split. And then if we initialize the system in the ground state, so in T minus, both spins pointing down, we can drive the system from T minus to singlet, T minus to T0, and T minus to T plus, that are the 3 lines you observe there. Then, as we have a strong interaction, we are driving singlet triplet qubits. So our states are not single particle, is not a single spin flipping, but the combination of 2 spins. Now, the question is, can we characterize from this the tilt between our 2 spins? Our initial question. The answer is yes. I don't have time to explain you the protocol, but basically, we developed a really simple protocol from which we can extract 3 parameters, and applying this formula where delta theta is how tilted our 2 spins are, we can plug in our values, and then we found out that the tilt is 45 degrees. That is rather large. And why is this important? So it has been predicted in this paper that basically if you have an anisotropic exchange interaction, that means a large tilt, the fidelity of 2-qubit gates might be larger for a C0 gate. So in this case, our spins are not aligned when our magnetic field is pointing in plane, in the direction of the chip. Now the second question, so our spins are not aligned, can we control this tilt? And the answer is yes, and we can do it in 2 different ways. The first way is just change the direction of the magnetic field. This data that I showed you before, the magnetic field was pointing in plane. For this plot, it's pointing out of plane, out of the slide. So again, you can see 1, 2, and 3 main lines, and applying our protocol, delta theta is smaller than 5 degrees, then that means that our spins are almost collinear and our exchange interaction is almost isotropic. And also we can tune this angle by changing the voltage in our electrostatic gates. So here you see 3 spectroscopies in plane, but changing the voltage configuration of our gates, even changing them up to 200 millivolts. And you can see that the tilt changes. And this might be also potentially useful for minimizing the leakage when doing 2-qubit gates with singlet triplet qubits. So with this, that is all. Our spins might be aligned or not, depending on the direction of the magnetic field, and we can also control the relative angle. And I wanted also to advertise a recent preprint with some collaborators in Oxford, where we are able to tune spin qubits with the help of machine learning. And I would like to thank our collaborators from QTech and Como in Italy, and also to all my group, and thank you for your attention.
Thank you. Any questions? Now is the time. No? Oh, yeah.
That's a good question. Maybe I can repeat it. So he asked, what are the extra lines that appear in the plots, right? Like that one there. So those are 2 photon, whoops. Those are 2 photon processes. And what that means is that basically that line, that the third line is always half of the frequency of the one on top. So in the fit, you can see the red line and the red dashed line. That one always has half of the frequency. That means that your spin is flipped. Instead of by 1 photon of a frequency of 100 megahertz, let's say, you have 2 photons of 50 megahertz. And that is enough to flip the spin state.
More questions? No? So in that case, let's thank the speaker again. Thank you. The next speaker is Gonzalo Martín. So Gonzalo is going to talk about the passive leakage removal unit based on a disordered Transman array. He comes from University of Seville, and yeah, the floor is yours.
Thank you. Thank you. So I did this work. During while working at the University of Oulu with Taneli Tolpanen and Matti Silveri, and this work presented here appears in this manuscript. So starting from the beginning, the qubit is a two-level system, but in many quantum computing platform is a subspace from a larger Hilbert space. So we call the leakage to the process that take the system outside this subspace. And due to many reasons, like applying gates or the measurements or even the thermal environment, and this complicates the quantum error correction because usually standard quantum error correction codes do not detect this error. So to get rid of this, we can reduce the creation of the leakage or remove the leakage when it's there by actively removing what is called leakage removal unit, or designing a quantum error correction code that take into account this type of error. So my work is theoretical and belongs to this second approach. The physical model is a chain of tunable transmons that are coupled by capacitance and are described by this attractive Bose-Hubbard model, where we have the local term, where we have the on-site energy omega and the on-site interaction, or also an harmonicity U, and the Hoping term J. So the bosonic excitation dynamics will depend on the interplay between these parameters. So in this case, the qubit states are defined within this restricted subspace there. And so if there is no excitation in one transmon, it's a 0 state. If there is one excitation, it's the 1 state. I mean, if there is a 2 or more, is what it's called leakage. In the rest of the talk, we will treat leakage just as a second excited state. So also, I will consider that the anharmonicity is different in each site and depends on the imperfection during fabrication, but also can be partially designed. The on-site energy can be adjusted by applying magnetic fields locally in the center of the squid. And Hoping terms is, we will assume it is homogeneous and smaller than the other. And disorder will be in general this the inhomogeneity in the parameters. So for the leakage removal unit model, it works as follows. So we have the transmon acting as a coding qubit, so it's the one that we are going to use for quantum computing, and then we attach a chain of either transmon that, and we are measuring the last one, but with a feedback measurement. So we measure the state, and then we apply a conditional gate, so we reset the state to 0 all the times. Also, a continuous dissipation will work, and I will show some results. So then we want to protect the qubit subspace there. So for that, we set the energies such as of resonance. So if there is an excitation in the qubit space, it will not propagate much, so the measurement will not have much effect. This is an example of a trajectory. And for the leakage, to remove the leakage, what we do is to set the harmonicity such that the energy of the second excited state is on resonance. So if there is a leakage excitation, it will propagate, and it will be effectively removed when we apply the measurement at the end. So then we test this with some numerical simulation, and we see here that the leakage population. So in the beginning, there is a leakage transportation due to collective propagation, and then there is a exponential decay because of the feedback measurement. So interestingly, it depends on the measurement rate that we were using. Here there are just two measurement rates. So, but we map many rates. So we saw that there were two optimal spots, and on these rates, the removal was faster and more effective. So also in the dashed line is shown for dissipation, engineered dissipation. In the following slides, I will focus for the feedback measurement and in the low spot, but in the paper there are the other cases. So for testing the performance, we calculated the dissipation and dephasing time for the qubit at the first site, T1 and T2, and also the decay time of the leakage in the whole change of transmons, what is the T star. So this is T1, T2, and this is the T star. So what we want is that these two values are as large as possible. So the qubit lifetime is large, and the T star is as small as possible, so we remove the leakage faster. So in this first plot, we show the effect of the disorder, increasing the disorder in the parameter, increase the T1 and T2 polynomially, and does not have much effect in the T star, and this is due to localization of the excitation because of the disorder. By increasing the Hoping term, we increase the mobility, so the leakage is removed faster because the effective propagation is increased, but also the qubit mobility is also increased, so has the same effect that we don't want this. And in this last case, we increase the size of the array, so we increase the number of ideal transmon in the middle. So the coding one, the measure one, and we increase transmons in the middle. And we see that it increased all the decay times. Well, for T1, T2 is exponentially, and for the leakage is linearly. Then we repeat the same, but with considering experimental feasible conditions. So we include dissipations and dephasing and thermal environment. And we also took into account the native T1 and T2 of the qubit. So in this dashed line, so we see how the leakage removal affect those values. So those are like the maximal value we can achieve in the experimental condition, and then we see how the leakage removal affect them. And we see something similar with some differences, but it's not that important. Maybe the important part here is to choose a set of parameters that we can perform in an experiment and give good value. So trying to increase T1, T2 and reduce T star, we found that these values are good, like 100 megahertz for the disorders, 5 megahertz for the Hoping term, and a leakage removal unit of 3 transmons. So the coding transmon, one in the middle, and the measure one, or the one with dissipation. And we see that the T1, T2 is not much affected. Well, it's affected, but this can still be corrected by quantum error correction. And the leakage decay time are of the order of a microsecond. But there's still room for improvement, and in the sense that if we increase the anharmonicity, we can include more disorders, so we can increase the Hoping term, so removing the leakage faster, keeping the same qubit protection. So it's something that can be improved. In this last part, we did some analytical studies. So some of to understand the physics underlying this and have a better control of the parameters. So some of the processes are understood already, like the qubit protection can be understood by localization, and the leakage transport by collective propagation with this effective Hoping term. So we focus in the existence of these two optimal spots, so we want to understand why this is happening. That also depends on this. And for that, we focus on the simplest case of just two transmons, so the coding one and the measure one. But in the paper, there are more generalization, but this is easier. So the idea is that the different excitations have different time scales. So for example, here we have a single excitation in one site, so it will hop to the second site. And this hopping will depend on if there is no disorder, it will depend on the Hoping term. But if we increase the disorder, this hopping will be reduced and its frequency increase. And if we increase the disorder more, it will be localized. For the leakage excitation, so we have two excitations in one site, then it will split into two sites, and then it will recompose at the other site. So we see here two time scale, the one fast disintegration and slow propagation. And in this case, it will depend on the anharmonicity. If there is no anharmonicity, there is not much sense in doing this difference. But if we increase the anharmonicity, we see that the disintegration is reduced and its frequency increase. And if we increase the anharmonicity more, we have this effective propagation, collective propagation. So with in the leakage removal unit using this parameter, we are in this case here. So we got this result where we saw that the low optimal spot corresponds to the leakage propagation, and is inversely proportional to the anharmonicity. and the high optimal spot corresponds to the disintegration and is proportional to the harmonicity. And also the optimal spot for removing the qubit excitation is proportional to the difference of the disorder. So we want to be far not there. So here we have the same map of different measurement rates, and we see how the population evolve in time. So in the beginning, the fast effect remove faster the leakage population or the qubits population, but then the slow one start to also remove the leakage population. And this is interesting in the sense that this is slow enough to be performed in experiment, and also is not affecting the qubit much, as we see here. For the dissipation, we have something similar, and even is more effective in this the low case. So summary, this is a scheme of how this leakage removal will work. So we have here two transmon acting as coding qubits, how we apply in gates. So if there is a leakage, we say the circuit is compromised in a sense that the standard quantum error correction code do not detect this type of error. So what we do is to attach a leakage removal unit to each qubit, and we perform the measurement with the rate found before. So then if there is a leakage appears in the circuit, it will propagate passively, and then it will be removed. So also this is interesting because this is always on. So even if you are performing the gates with discrete time, this is leakage removal is always on in the background. And even changing the feedback measurement with an engineered dissipation, this is fully passive. So in conclusion, this unit can be generalized to other devices with similar energies and coupling structures. And it requires a simple hardware in a sense that it requires more of the same, like just more transmons. There's no need of a filter or something. It's passive. It's different from other methods, but being passive is a bit slower, but also you don't require apply impulses or anything to the qubit, coding qubit. And it can be scaled for many different scenarios, like two-dimensional grids where the leakage removal unit are on the border. And well, this is a numeric analytical study, so it will be nice to see if this works in experiment. And now we are working in the larger system and including the quantum error correction code to see how they work together. And this is the
Any question?
Thank you very much for your presentation. Do you know, or do you think you could apply your analysis techniques to study higher order anharmonicities, or do you think, on the other hand, that a Bose-Hubbard model captures like most of the interesting physics already?
You mean like considering 3 excitations?
Yeah,
or
for instance.
Yeah, so this could work in that sense. You just need to match the you will need to match to make on resonance the third level in that case. So for example, if you want to remove the second leakage of 2 excitation and leakage of 3 excitation, you can set this for the 2 excitation, and the other side do the same but with the 3 excitation. So you make the level 3 on resonance with other leakage removal. So the 2 excitation will move to one leakage removal unit, and 3 excitation will move to the other leakage removal unit. But yeah, I think I don't know how how efficient or if it's interesting, but at least it could be done. Like, you just need to make them on resonance.
Okay, thank you.
Any other question? I have one. Do you know how this disorder chain of transmons can be engineered? I mean, can you engineer disorder? Because I guess that's a drawback, at least for experimentalists.
Yeah, this was as a way of using the disorder for something good. Like, so I explain it here in a different way. Actually, what you have is disorder in the anharmonicity, and then you can adjust the disorder in the energies. But so as far as I understood, is that you have a disorder and you want to reduce it, but here is we encourage to use disorder and even engineer it, trying to add as much as possible of the anharmonicity. So then you can add more disorder in the offside on the energy, so you can have more qubit protection.
So it's different anharmonicities for different transmons.
Yeah, yeah, sure.
That's the meaning of the disorder, you mean?
Yeah, yeah. So when it's built, what you have is the different harmonicity in different transmon, and then you use you apply the magnetic flux to set the on-site energies. But the anharmonicity are already set in the fabrication. But I think it can be at least using our parameters. We took the parameters from what has been done. So at least I think.
Thank you. So, no further questions? So let's thank the speaker. Thank you.
Okay. Next speaker is Carlos Payá from ICMM, and he will talk about a fluxoid valve affecting full shell nanowire Josephson junction. So the floor is yours.
Thank you for the introduction and for having me in this conference. So first, let me introduce myself. I am the PhD student of Ramon Aguado and Elsa Prada here at ICMM, that mysteriously is located in Madrid, as its name says. And most of the work I'm going to present here has been done in collaboration also with Pablo San Jose, also at ICMM. Part of this work has been done in a cross-parking lot collaboration with FJ here and Alfredo at IFIMAC, and can be found in these two papers, one of them still in peer review, and the second one is published in PRB. So, I want to show you how full shell nanowires junctions can work as magnetic field controlled supercurrent valves, which is a new effect that we have introduced in that preprint that I showed you before. And for that, I'm going to answer two questions. How does ready mismatch in a full shell junction affect the supercurrent that we can flow through it? And what happens when we have Majoranas? Because, of course, this session is about qubits or things related to qubits, so I have to talk about the M word in full shells. But first thing, why do we care about full shells? Maybe some of you have heard about Majorana nanowires, which is these devices that I present that you can see here that were proposed back in 2010 and are in fact the same wires that Alberto is using for his Purman's key-type chains. But here the origin of the Majoranas is slightly different, is topology. Here we're basically engineering a situation with our bands in which we have, thanks to a spin-orbit coupling and a Siemens field, we are able to manage this situation in which we have two bands that are spin-locked. That means the spin is fixed to the momentum, and with chemical potential we can tune ourselves to a situation in which we isolate one of those bands. So that band is effectively spinless. If we add particle-hole symmetry to this through superconductivity, what we have is basically a somehow equivalent to a P-wave superconductor that can undergo a topological transition, and the edge states of a P-wave superconductor of a topological superconductor are Majorana zero modes. So let's just build the device and tune it to these parameters, and then we have Majoranas that are not Purman's Majoranas, not working class Majoranas, but Bill Gates level Majoranas. But of course, as everything in life, this has a lot of problems. One of them, for example, is charge noise from the environment. Basically destroys all of this, and it's very difficult to find Majoranas in these systems. These wires on the profile look like this. We have a semiconductor, indium arsenide, indium antimonide, or whatever, and this is partially covered with a layer of aluminum. In general, they have a hexagonal profile, and we also have an axial magnetic field. So An idea to try to solve at least this problem of charge noise was to cover these wires completely with a superconductor. And now they are completely isolated from every charge noise that we can have around the device, precisely because this is a metal at the end of the day. And this is precisely what Solevay-Tiekenas did in Charlie Marcus' group back in this beautiful paper in 2020. And this is the first experimental insight for what I'm going to talk today. These wires, apart from being protected from charge noise, they also have a topological transition at far lower magnetic fields than their partial cell counterparts. How do we model them? Well, basically, we have a semiconductor core and a superconductor. And this, if you do the electrostatics problem, shows a band bending profile like this. And thus, we're going to have charge concentration close to the interface between the semiconductor and the superconductor. This, plus cylindrical symmetry, will allow us to model this in very efficient ways and obtain even analytical results and predictions on the full cell wire. So, let's, before studying the Josephson junction between two such wires, let's study a single wire just to have some things clear about what happens here. So if I do a transport experiment on one of these wires, let me forget about the other end. Let's just focus on what happens at this interface. So this wire is effectively semi-infinite. The first thing I'm going to observe is that my superconducting gap is modulated in this way. This is a thing very well known. It's called the Little-Pax modulation, and it is due to the fact that we have a doubly connected superconductor. And if you look closely, you will realize that the maximum of this modulation is at integer values of the flux quantum, and the minimum is at half integer values. Okay, so this modulation was predicted back in the 60s, and it's a very well-known effect of cylindrical superconductor. But here we have two materials, not only the superconductor, we have something inside, we have indium arsenide inside. So some states will live inside indium arsenide, and they will show inside the gap. If you think about these wires as an analog to a vortex of a type 2 superconductor, because at the end of the day, it's basically the same idea. If you take a type 2 superconductor, you choose one of the vortices and cut it somehow, you get a geometry pretty similar to this. And the states that you get inside a type 2 superconductor vortex are the Caroli-de Gennes-Matricon states. So here we have something similar, some related physics that also allow us to have states inside the gap, and that's why we call them Caroli-Gennes-Matricon analog states. These states happen to be degenerate, all of them. We have many of them. It depends on the parameters of the wire, how many of them we have, but all of them are degenerate at integer values of the flux quantum, like the Little-Pax effect. That's called the degeneracy point. However, these states are not located at the superconductor. They have an effective area that is smaller than the effective area of the superconductor. And at the end of the day, what controls this modulation is precisely that area. So there will be a mismatch between the periodicity of the Caroli states and their degeneracy points and the Little-Pax modulation. Thus, we will have skewed Caroli states. We'll have, if we do a transport experiment, we would see this skewness, and we will also see this shifted superconducting gap. By the way, I forgot to mention, we call these structures Little-Pax lobes, and they are associated also, okay, the integer value of the flux quantum, or this number that we see here, is also the winding number of the superconducting phase. This is not just theory, it has been recently demonstrated experimentally by us in collaboration with Charlie Marcus and Solevay-Tiekenas and Ming-Tang Den at the University of Copenhagen, and has been recently published at PRL, and you see that the match between experiment and theory is beautiful. It's a very beautiful paper. I recommend you to read it if you want to learn about this. But now, this talk was about a Josephson junction, so now let's take two of these wires and all the physics we have learned about them, which is, for the moment, unrelated to Majoranas, and see what happens. And this is going to be a kind of this special Josephson junction in which the wires have different radii, and this is going to be important, as I will show in a second. This is just a theory model, so it's going to be a short junction. That means that this length is way smaller than the superconducting coherence length. We are going to be able to control transparency somehow in the junction, and this is going to be just the DC Josephson effect, okay? No voltage bias in these calculations. Doesn't work. It's frozen. Well, the computer is having some trouble. Oops, spoiler. Okay, so now let's explain why this works as a valve. Here at the left-hand side, if I thread it with with a magnetic flux, I'm going to have a superconductor winding number. The phase of the superconductor is when I wind with a given number that is related to the radius of the superconductor and to the magnetic field. And of course, at the other side, I have another radius, so that winding can be different, or depending on parameters, might be the same. So it can be checked theoretically that there is no possible current flow if those two numbers are different. Why is this? Because at the end of the day, if I add a phase bias between these two segments of the junction, as I do in a Josephson junction, I can translate that phase bias into a rotation of one of the cylinders. So I can rewrite the superconductor order parameter in this way, in which this phase bias is just an angle, an actual real space angle, an actual real space rotation. But there is cylindrical symmetry, and thus this angle variation cannot change the free energy. The free energy is going to be the same because of the cylindrical symmetry. And if the free energy is the same, the derivative of the free energy with respect to the phase is 0, and thus my Josephson current is 0, my critical current is 0. This mechanism allows for a current flow if both fluxoids or both winding numbers are the same, because then, of course, this stuff doesn't work, and then I can have a current as I would have in any other Josephson junction. If we do the simulation, like with the full numerical code and so on, what I have here is the local density of states at this side of the junction. Down here, the local density of states at the other side of the junction. And if I calculate the critical current, I see precisely that. When those winding numbers, that's when these two lobes overlap with different windings, this is winding 1 and this is winding 0, I have 0 supercurrent. Same here. Here I have winding 2 and here I have winding 1, so supercurrent is 0. And the rest of the current where the windings coincide, can be explained through the Carolys. It's due to if you see here, the Carolys are skewed to the right, and thus the critical current is also skewed to the right. If I add some kind of, for example, a gate here in the junction, that means worsening the symmetry of the junction, and that opens these valves. It worsens the valve, but we do not recover a full supercurrent. It's still suppressed. So this is the fluxoid valve effect. What happens if we have Majoranas now in the junction? Well, nothing very interesting, to be honest. It's just the typical behavior of the Majoranas. Majoranas are 0 modes at the edges of the wire, and that means they go their conductance doesn't go with the transparency, but with the square root of the transparency. So if I have Majoranas at both sides of the junction and I'm in a tunnel regime, then the valve effect is going to be seriously increased, as you can see here. But this is not surprising. This is what we expect exactly for Majoranas. Let me remind you that the full story I've told you here is available in this preprint, and there are experiments ongoing by Jesper Nugo at Copenhagen and also by Eduardo Lee here in Madrid. Just a little bit of a spam. My bachelor student, Cesar, is here, and he has a very interesting poster about fake Majoranas in full shell wires. Let me also tell you that all these calculations have been made with the Quantica package, so if you are into tight binding and Green's functions formalism, you should check this on GitHub by Pablo San Jose. And with this, I end my talk.
Okay. Any questions? No?
Cool. Well, if nobody. Thanks, very clear and useful. Can you go back to the supercurrent? So here, so I get the spin valve, the supercurrent valve effect, so when it goes to 0. But if you look between 0.1 and 0.2, there is an increased trend,
Yes.
right? And I would expect exactly the opposite, because I would expect more supercurrent if the state is closer to zero energy, if your
But
analogs are closer to zero energy.
If you see the local density of states at both sides, you see that the gap, the superconducting gap increases as I go to larger magnetic fields. So the supercurrent intuitively must be larger.
So it's going through the gap, you say,
Yes.
not through the Carolis.
No, but the Carolis are also away from zero energy. This is the Caroli.
Sure, but
And
they should help the supercurrent.
They give you the supercurrent through their gap. Which, the supercurrent is not related to where this state is, but to this gap. How large is this gap?
Yeah, exactly. That's my point. So the gap becomes larger, so you should get less.
No, if your gap is larger, then you get a larger supercurrent. If you have zero gap, if you kill superconductivity, like here, I don't have a gap here, then I cannot have a supercurrent for that mode, for example. If I have no superconducting gap, I cannot have a supercurrent because there is no superconductor.
Okay, I think we have a little bit of a different picture, because I see it as well, maybe we can discuss it offline, but I see that as a virtual excitation. So in that case, the higher the gap, the worse it is.
This is a ground
But
state. We are in the ground state for this. We can discuss it later if you want.
Yeah. Do it.
Perfect.
Okay. Any other question? No? Okay. Let's thank the speaker again. And the next speaker is Niccolo Valdelli.
Para el tipo de láser.
Okay, so as I said, next speaker is Niccolo Valdelli, and he is going to talk about fragmented superconductivity in the Hubbard model as solitons in Ginzburg-Landau theory.
Okay, thank you for having me here and for being here. So compared to the previous ones, this is going to be a bit more of a theoretical computational talk, and as you can see, there are a lot of complicated words in the title. I hope they're going to be a bit more clear by the end of the talk. And all the results of this talk are based on this paper here that you can find here. And they have been produced with amazing collaborators in New York at the Flatiron Institute and in Dresden at the Max Planck Institute of the Physics for Complex Systems. So the building block, the basis from where we start for our investigation is the Hubbard model. So we're just taking electrons hopping on a square lattice with on-site interactions. And the question we're asking is there possibility to have some kind of superconductivity just in the framework of this model? There have been a lot of investigations in the last 50 years, but actually in 2020, through numerical calculations, we discovered that it's actually impossible on the clean Hubbard model on the square lattice to have any kind of superconducting order. However, this is valid for any doping. So you start from an half-filled model, so you have an electron per site, and then you add or remove electrons, and you have the same situation. However, what the community realized after is that if you add a bit of frustration, so if you allow the electrons to jump to further sites, you can actually stabilize a superconducting phase in your model. And this is a pretty recent result and is valid for either electron or hole doped systems. However, even if we know that there can be some stabilization of superconductivity in the Hubbard model, the phase diagram of the system is still extremely debated. For example, you can see here that you have a proposal for a temperature doping phase diagram, and there are some phases, and then there is another proposal for the zero temperature phase diagram, and they're not compatible one with the other. For example, here there is a stripe order that here does not appear. So what we're trying is to shine light on a particular zone of the phase diagram that's exactly here. So we're trying to understand if this stripe order, that's basically a modulation, a periodic modulation of the electronic charge, is somehow linked to the superconducting order. And this is something that appears at zero temperature and at like a finite doping somewhere here. So usually, how do you, and the way we did this is numerically. If somebody is familiar with tensor networks, we just use DMRG, density matrix renormalization group. It's a pretty standard tensor network method where we try to map our two-dimensional system in a one-dimensional chain, and then we can compute the ground state of the system with a really good approximation. And with the thing we're observing, we're looking for is this superconductive pairing, this D-wave superconducting pairing, and the hole density. And this measures our superconductivity, and this measures our stripe modulation. And so I was saying, how do you usually measure superconductivity numerically? This thing numerically is always zero, because you know that this is not a charge-conserving quantity, and you're working with a fixed number of particles in numerical calculations. So what you do is just look at the off-diagonal long-range order of this superconducting order parameter, and if you have an algebraic decay of this quantity, you're an order phase. Otherwise, you're not in an order phase. And this is what's usually done in the literature, but we use another way. So it's like a parallel path to obtain the same thing that can give us more insight on what's happening. And we're using this thing that's called the Penrose-Onsager criterion. So this is a criterion that was initially developed for Bose-Einstein condensation. And it's really easy and says, imagine that I have a bosonic system. These are bosonic operators. You compute the one particle density matrix. These are like, for example, positions in a lattice or another or a lab of another basis. You diagonalize, and this is like the average on the ground state of the system. You diagonalize this matrix, and then if you have that one or more eigenvalues of this matrix is much bigger, and this much bigger is like an heuristic statement, is much bigger than the others, that means that there is some Bose-Einstein condensation. And so we try to use the same approach for Cooper pairing. So we say, okay, let's take the pairing operator, compute the same thing, and then we say if there is one or more eigenvalue that's much bigger than the others, that means that we have Cooper pair condensation in our ground state. And the interesting thing is that what we find is that we have a fragmented superconducting ordering. That means that this pairing, this condensation of pairs, doesn't happen in a single channel, but it happens in different channels. And so what we're asking is, what's the meaning of these channels, all right? And so the first thing that we can see is that if we compute both, the charge ordering of our system, that's this gray line. This is like an average along the y direction, and this is like a picture of the system from the top, okay? If we look at the charge density behavior and the number of condensate, they are the same. So there is like one superconducting condensate per stripe. And the other really interesting thing is that these condensates that are these red or blue lines have some periodicity that's compatible with the periodicity of the of the charge modulations. And so the other question we're asking is, okay, we know that these eigenvalues tell us the number of fragmented condensates, but what are the meaning of the eigenvectors of this density matrix that we're diagonalizing? And usually in Bose-Einstein condensation, these are just the wave functions where your bosons condensate. But here it's not really clear what's going on. And but what we saw is that we can develop a really, really straightforward Ginzburg-Landau free energy functional that's dependent on the charge order, and we can actually recover our eigenvectors of this density matrix that we get from numerical simulations just by computing the minimum of this functional. And these are actually these red lines that are superimposed to the blue ones that are the ones that we compute numerically. Okay, and for example, so the way we compute this minima is just we use different ansatses for this functional, and we realize that different local minima of this functional correspond to different superconducting fragments. Here, for example, you can see our system. This is like a 24/6 lattice. Here, these black holes are like the stripes I was talking about before. So these are these density modulations, and you have that your superconducting order localizes on these holes, and is well described by this minimum of this functional. And actually, you can see that you can kind of get, even in this picture, the same behavior both from the numerics and from this theoretical ansatz, even in the presence of a magnetic fields, the threads in the system that impresses a phases on the superconducting order, and it is the same on both the numerics and the analytical results. So to conclude, what we did is to obtain these properties on the square lattice using an approach that's different from the one that was used before. So that was this of diagonal long-range order. We used this Penrose-Sager criterion instead, and this can lead us to unveil a further property of superconducting in the Hubbard model, that is this fragmentation. And the fact that we can understand this using an effective theory can lead us to a better understanding and also to expansion of this idea without the need of further numerical investigations. And that's it. Thank you very much.
Okay, thank you. Any questions?
Thank you very much for your talk. Towards the end, I'm not sure I understood all of the details correctly, because you said that I believe you used an ansatz to solve your Ginzburg-Landau problem. So essentially, did you do some sort of variational calculation, or what exactly?
Yeah, I was a bit fast on this. So the idea is that you just define this functional on a grid, okay? So your target is this psi, okay? That's like two-dimensional wave functions, and you define it on a grid, and then you start, for example, as an initial ansatz for this psi. You can either use this, that's like a constant value, or this one that's like with a with just one node. This is a modulation. These are like positive values and these are negative values. And then you run normal variational minimization algorithm to find the minimum of that functional using that ansatz. And depending on the ansatz of the periodicity of the ansatz, you find a different local minimum. And this perfectly reproduces the different fragments of the superconducting order.
Okay, and I guess just like an extra question, was there any particular criterion for choosing those ansatz? Or?
It's periodicity. So the thing is that we see that the periodicity of the stripes, the periodicity of these fragments are like, for example, the first one is periodicity is like uniform, the second one is periodicity pi, the second one is 2 pi, something like that. And so we use the same periodicity and we recover the same results.
Okay, thank you very much.
Any other question?
Thank you. Sorry, but I lost track of the frustration parameter at some point. The frustration that you have to include to have superconductivity. So you only need to have it finite, infinitesimally finite.
Here?
Yes.
So usually, and this is like given, so the reason why we set certain parameters is just to get the same parameters that they use like in corporate simulations or experiments.
Okay.
And this is like, if this is 1, usually this is like 0.2.
Thank you.
Yeah.
Okay, so I think time's over. Let's thank the speaker again. And talking about fragmentation, we have to split in 2 groups, more or less, for the land. So there is one canteen right there, and another more. You can follow us, and that's all. I think we can come in 1.5 hours, and that's all. Thank you.
Lo iba a apagar. Ah, lo ibas a apagar. Bueno. Sí, no, bueno. Estos ya han presentado todos. ¿Cómo? Es tuyo. Este es de aquí, pero yo tengo el note aquí puesto. Ya, bueno, en realidad lo podemos. ¿Para qué no? Sí, para que no. No, mejor la de aquí. La verdad que me pago. Lo decía por. Con que le llevemos. Por. O no tiene sentido. Dejarlo encendido. Está cargando, ¿no? Sí, bueno, es igual. En realidad es igual. Bajamos. ¿Se enciende aquí las luces de la pizarra? Sí. Sí. ¿Qué barbaridad? Sí. Es una locura. Sí. Dale. Tenemos que empezar a ir saliendo si queréis y... Pero decís por algo lo de las luces, no porque... Para algo porque Carlos va a usarla un poco. Mira. Entonces yo creo que estas de aquí hay que... Así, ¿no? Así. ¿Así se ve bien? Es que me parece una locura esto, porque puedo poner el modo conferencia, que es una locura. El orador, que es solamente aquí. Es solo aquí, mira. Y si la vamos cambiando durante la charla, sería top. Pero... Mira, pum. Mira. Brutal, tú. Pero la diferencia es ínfima, pero está guapo. Sí. Bueno, también... Si usa la pizarra, los que lo estén viendo por YouTube no van a ver una mierda. Ya, eso es verdad, pero bueno. Yo es todo. Pues ala, vámonos. Vale, dejamos. Descargamos la. Manda un correo. La charla de Carl. Ah, vale. Igual la ha metido en los. No. Que puso 2 diapositivas la última. Mira ahí está.
Hola.
Yo creo que la pizarra lleva sin usarse años, ¿eh?
Pero se veía súper bien.
Pues por eso, porque es nueva, completamente nueva.
Hola.
Dale al de arriba. ¿Al de arriba?
Wow, estás ya hecho a la sala.
¿Nos parece como que tenía mucha saturación este? O no sé.
Hola.
O era este. Hola, hola. Oh.
Están ahí fuera.
Yo qué sé. No sé cómo va.